100 years ago, one visionary set forth upon a scientific journey of the mind so profound that it forever changed the way we live our lives and view the universe. Practicing physics on the sly, and with very little personal interaction with the scientific establishment at the time, this unknown patent clerk in Bern, Switzerland, named Albert Einstein, wrote 5 seminal papers in 1905 that encompassed the whole of the universe, from the workings of the atom and out through space and time. During the course of that 1 year, the brash 26-year-old Einstein helped clinch the then controversial case for the existence of atoms. He proposed that light is made of particles of energy, and he began to turn the tables on Isaac Newton's laws of motion, laws revered for more than 200 years. He said that space and time were relative depending on one's frame of reference. Traveling at light speed, time slows down so that 1 second will linger for an eternity. He also realized that matter and energy are interchangeable. E equals mc squared. Einstein's theories set the stage for the technological revolution that defined the 20th century. Lasers, electronic sensors, nuclear fusion, all point back to one man and one miraculous year.
Einstein had a way of working, but it was really his stubbornness that made him stand out. He didn't take for granted what other people were saying. He realized that gravity was different from all the other forces of nature. General relativity says that gravity is not a force, but it is a feature of space-time.
Einstein's theories on gravity, space, and time led to startling outcomes that in some cases Einstein himself could not believe. The universe is expanding and is not static, as was thought at the time. We now believe this expansion is caused by a Big Bang. His equations also revealed that regions we now call black holes can cause space to buckle and bring time to a halt. Recent technology has propelled an explosion of new findings, raising new questions that Einstein's theories do not address. What powered the Big Bang? What happens at the edge of a black hole? And what is the mysterious dark energy that is now accelerating the expansion of the universe? We've been at such crossroads before. The scientific revolutions spawned by Isaac Newton and Albert Einstein were a result of the growing inadequacy of established theories of their times.
We're sort of at that stage again, where despite our vastly more sophisticated understanding now than in 1905, we now have results primarily obtained from astrophysical observations, which are simply not accommodated in our theories.
This is where NASA's Beyond Einstein program begins. Scientists have set a course, a well-coordinated mix of facility-class spacecraft, probes, and Pathfinder missions, each with powerful new technology to explore the extremes of nature, the Big Bang, black holes, and dark energy. For it is here that the current theories begin to crack and answers are revealed.
To really understand the laws of nature, we have to go to these extreme environments and study them to give a hint of the true fundamental laws of nature.
People are talking about doing precision cosmology for the first time. Because it used to be cosmology, well, we have a rough idea how big the universe is, maybe to a factor of 2 or 3. But now with these new measurements, we're really getting a handle on the overall density and structure of the universe. And what they're telling us is not what we expected to hear.
Well, the biggest mystery today in all of science is dark energy. Why is the universe speeding up? It's a fantastic puzzle, and we're quite confident that when we figure it out, it's going to give us answers about other important puzzles as well.
Since 1998, something totally unexpected happened, which is we discovered that not only our universe is expanding, this expansion is accelerating. This is a classical who ordered that type situation. 70% or so is dark energy in the universe. About 70% of the surface of the Earth is covered with water. Imagine we didn't have a clue what water was. This is the situation we're in.
A mysterious force propelling the universe? Ironically, Einstein proposed such a force to counter the inward pull of gravity and to keep the universe static, which was the belief 100 years ago. He called this the cosmological constant, a vacuum energy of empty space. When Edwin Hubble discovered the expansion of the universe in the 1920s, Einstein called the cosmological constant his greatest mistake. But the mysterious dark energy we see today may well be a manifestation of this cosmological constant. Einstein was perhaps right, after all. Richard Feynman and others, who developed quantum theory, realized that empty space was full of temporary or virtual particles continually forming and destroying themselves. Physicists began to suspect that the vacuum of space ought to have a repulsive form of energy generated from these virtual particles, but they could not predict its magnitude. We still do not know whether the highly accelerated expansion in the early universe called inflation and the current accelerated expansion due to dark energy are related. A space-based mission called the Dark Energy Probe, to be jointly implemented by NASA and the Department of Energy, is being planned to measure the expansion accurately enough to learn whether this energy is a constant property of empty space, as Einstein conjectured, or whether it shows signs of the richer structure that is predicted in modern unification theories. This mission will be a major step in tackling the mystery of dark energy.
For the first time, we actually have an inventory of the universe. But if you look at the accounting, 95% of the stuff is in forms yet to be fully understood. And so we know a lot, but we understand much less.
And among the 5% that scientists call ordinary matter lie yet more mysteries, the most perplexing of which are black holes.
Black holes are the strongest test of what the theory of gravity really is. Space is just bent and warped and twisted in some incredibly complex way. And if one could only understand that, one would have a fundamental insight into the theory of gravity.
In the past 5 years, our knowledge of black holes has really exploded. By using space-based and ground-based telescopes covering the full electromagnetic spectrum, astronomers have found that black holes are everywhere. They come in a variety of sizes, and they are integral to the formation of galaxies. One way to find a black hole is to look for X-rays that are produced by matter caught up in its violent and extreme environment. In fact, we are extremely close to looking at the very edge of a black hole, something Einstein never imagined.
What happens to matter and energy as it moves closer to a black hole and crosses the event horizon, the theoretical border from which nothing can escape? Does time really come to a standstill? Will we see a breakdown in general relativity in the environment of extreme gravity? General relativity makes specific predictions about matter and energy close to a black hole. If, upon close scrutiny, we see the slightest deviation between theory and observation, we will understand limitations in Einstein's equations. 2 space missions will take us closer to a black hole event horizon than we've ever been. LISA, a joint NASA-European mission now in formulation, will listen for gravitational waves created by merging black holes.
Now we're talking about opening a window that's not even based on electromagnetism. It's a window that's based on gravitational radiation.
The gravity wave spectrum is kind of a new and really unexplored frontier. No one's directly detected gravity waves. As we start to open up this next frontier, which I think many of us think of as the great frontier for 21st century astronomy, I think we're going to learn about different things from different parts of that spectrum.
Another mission will give us a closer look at black holes and probe the mystery of dark energy. Constellation X, an X-ray observatory, will make movies of the material falling into a black hole to map the warping of space-time.
Constellation X will let us watch how that matter approaches the event horizon, and how, from our perspective, time creeps to a halt. We'll be able to watch the final X-ray flicker of light as matter plunges into the black hole and disappears forever. This is where we'll be able to probe the most extreme conditions of gravity that we know of and really put Einstein's theories to the test.
And we plan to probe deeper. In 1992, the NASA COBE mission discovered slight temperature fluctuations in the nearly uniform cosmic microwave background. That's the blanket of light encompassing the universe that is the afterglow of the Big Bang. COBE's successor, NASA's WMAP mission, produced this much higher resolution image of the cosmic microwave background, becoming one of the most scientifically significant images of cosmology today.
When we look at the WMAP data, much of what we see in the data has the imprint of the physical processes that took place about 300,000 years after the Big Bang. The basic properties that we've inferred from this is that the geometry of the universe is flat or nearly flat. We also know it's pretty old. Today we know it's about 13.6, 13.7 billion years old, and the stars formed about 100 million years after the Big Bang.
The information obtained by WMAP and proposed missions will help distinguish between competing theories of what sparked inflation and the Big Bang. Einstein hoped to fold the quantum force of electromagnetism into general relativity and to find a unified theory. Much of what he could not answer and struggled with until the day he died remains unanswered today. These questions about dark energy, black holes, the Big Bang, and the nature of gravity have come to define the cutting edge.
The next revolution that I think could be in the not too distant future is to really learn what space and time actually are. And I think, as do others, that we will learn that space and time are not fundamental. There are more fundamental entities that make up space and time. And when we can figure out what they are, the atoms, if you will, of space and time themselves, I think that will take our understanding of the universe to a completely new level. And I think that discovery may be on the horizon.
Like Einstein's theories, modern theories make fantastic predictions that seem hard to believe. Unseen dimensions and entire universes beyond our own. We must find facts to confront and guide these new theories. Thus, we follow matter to the very brink of black holes and detect particles of time left over from the beginning of the universe. And we will use breakthrough technologies to see beyond the vision of Einstein to the uttermost extremities of existence.